Our cake is cooling, so that 10 minutes after it is removed from an oven, its temperature is theta Celsius. When the cake is removed from the oven, its temperature is 160 Celsius. After 10 minutes, its temperature has fallen to 125 Celsius. To understand this problem, I just want to concentrate on this sentence over here, where we're told that the cake is removed from the oven and its temperature is 160, and after 10 minutes its temperature has fallen. We need to visualize this. One way to look at it is to draw yourself a horizontal line and say that at the beginning of time our temperature was 160 and it cooled down to 125 degrees Celsius. Now, let's have a look at it in terms of the time. So we know that this happened from time 0 to time 10 minutes. That's our time here. If I was to divide this time equally into 1 minute intervals, we could also know what the temperature drop is from 160 to 125 every minute. But mathematicians do not see it this way. They like to put things in graph form, where the vertical line is going to show us the temperature and the horizontal line is going to show us the time in minutes. So we can see that our cake is cooling from 160 to about 125 here, and it's doing this over 10-minute period, so that our temperature decrease will look something like this. Now the difference between the first model that I showed you and the second one is that we can see that there is a gradient, which is showing that there is a decrease in temperature, so that the difference d theta, the little change in the temperature over the change in the time, this gives me a gradient. Did you notice that the rate of decrease of temperature therefore is constant? Now this is just a model, a very simple model, and they tell you that the rate of decrease of the temperature of the cake is assumed to be constant. So we are looking at a straight line. In that case, the change in temperature over the change in the time is equal to some constant. And because the gradient of that line is negative, we'll put a negative sign and we'll say is that this constant is a positive constant. Now this is a differential equation. This is the answer that you want to receive that 1 mark here. So what we found was the gradient. Now if we want to solve this differential equation to find theta, we need to integrate that gradient in terms of t. Integrating minus k, and we'll put the k in minus in front, with respect to t, we'll get k minus t plus the constant of integration, which is c. So theta is equal to minus k t plus c. Now we could find out what the k is and the c with the information that we were already given. And we know that at t is equal to 0, our theta is equal to 160. That's from the information above. In that case, we can say that c must be equal to 160. And so now our theta has a little bit more information. It is minus k t plus 160. And we also know that when time is 10 minutes, we know that our theta is equal to 125 degrees. So substituting that into our equation, we have 125, which is equal to minus k, t being 10, plus 160. And solving for k, I'll put it on the other side, minus 10k is equal to 160, take away 125. That gives us minus 10k equals minus 35. So k equals 3.5. And when we substitute all this into our equation, we will get minus 3.5 t plus 160. So just to remind you, solving requires you that you find the k and the c. So what is the one limitation of this model? Well, the model CS says that the temperature decreases at a constant rate, and we can see from our equation that it always decreases by 3.5 degrees every minute. But it doesn't account for the decreasing temperature difference between the cake and the surrounding environment. For instance, let's say that you've just baked a cake and it was a very, very hot day, such as 40 degrees. The cake would be cooling at a much slower rate. But if the temperature of the house was now, say, around 0, you can see that that surrounding temperature is going to influence the rate that that cake is cooling. It'll cool a lot faster. So this model assumes a constant rate of cooling, which does not account for the decreasing temperature difference between the cake and the surrounding environment. In a revised model, the rate decrease of temperature of the cake is proportional to the difference between the temperature of the cake and the temperature of the room. And the temperature of the room is said to be constant 20 Celsius. So we're going to write another differential equation for this revised model. So now our differential equation, d theta over dt, is proportional to the temperature minus that 20 degrees of Celsius. And where we've got a proportional sign, we can now change it into an equal sign by saying d theta over dt is equal to minus k theta minus 20. And that's it. That's where you get your mark for this differential equation. Now, just like before, we need to solve this equation, which means that we need to find what k is and obviously the constant of integration once we integrate it. Now, the reason that it's got a whopping 6 marks is because it's going to require a lot of algebraic calculations. I'll rearrange the above equation so that it'll look like this. 1 over theta minus 20. I've moved that to the left, d theta. And that's going to equal to minus k dt. Now I'll integrate this side and I'll integrate this side. And I should get ln, because that's what it'll be, theta minus 20 is equal to minus kt. All right, now I said that when you integrate, you need to have integration constant. So I could put an integration constant here, an integration constant here. Now we don't usually have 2 integration constant. 1 is enough. So we'll only keep the 1 on the left because it's just a constant. And it'll look like this, plus c. Now I'll just remind you that e to the ln is just equal to 1. So all we need to do is to write down theta minus 20 is equal to e to the minus kt plus c. So I need to solve c, the yellow one, and I also need to solve k to be able to find what this equation is. I have chosen to continue with it in this manner, but I could have actually stopped right here and looked for K and C. From both of these sides, I would still get exactly the same thing. So I'm going to actually do it both ways, just in case you thought you might wanted to do it the first way. All right, so let's start with the first one here. At T is equal to 0, our temperature is 160. And the same thing goes here. At T is equal to 0, our temperature is equal to 160. So on the left-hand side, we will have ln. 160 take away 20 is equal to 140, which is equal to minus k t, which is 0. So that becomes 0. And we now add the c to it. So let's just finish this off. And we have ln 140 is equal to c. So we found what c is. On this side, on the other side, we have again, we've got 140 is equal to e to the minus k, and this was 0 here because we had at temperature 0, plus c. So what we get is 140 is equal to e to the c. All right, so that means it's the same thing as saying that ln 140 is equal to c. So as you can see, we needn't have gone that 2 steps forward as I did, but this is the beauty of maths. Any way you do it, you'll get to it as long as you're doing the right algebraic movements. And now that we know that c is ln 40, we can rewrite this again, and we can say ln theta minus 20 is equal to minus k t plus ln 140. I'll use the left-hand side solution to continue. And we also know that when t is equal to 10, our temperature is going to be 125. And substituting those, we'll get ln 125 take away 10 is 105. And minus k. And the temperature at this point we're saying is 10. And we still add ln 140. So ln 105 take away ln 140 is equal to minus 10k. So we'll change. So that means that ln 105 over 140 is equal to minus 10k. ln 0.75, which is minus 10k, and therefore k must be equal to, all right, well, I'm going to substitute that k into here, and so that you can see everything, I'll continue writing on the right hand side. So we have ln theta minus 20 is equal to minus 1/10. Remember, you've got 2 minuses now here. ln 0.75. Let's not forget that there's a t there. Plus ln 140. And I rewrote this again. So to get rid of the ln on the left-hand side, I'll take it up to the power of e, so that'll be... Now remember that the whole right-hand side has to be raised to the power of e, not just each one individually, so I'll need to rewrite this all here. This allows me to write down that theta minus 20 is equal to e to the power of 1/10. Now, ln 0.75t. But now I'm going to, because this is an addition here in the powers, so I can multiply that by e to the ln 140. And once again, that cancels out, and we need to rewrite, which can be finally written as theta is equal to 140. That's why you get 6 marks for this differential equation. Okay, remember to subscribe and like it, and have a wonderful day.